Okay, so let's see if I can find my pointer here. We're gonna think about these different terms one at a time. I guess let's start with the forces. So if you think about the x forces, right? This is an x momentum balance. So the x forces on this control volume include the pressure. So there's a pressure force on this side. It's at the x. It's at location x, and it's in the positive x direction. And if I go to the other side, there's a pressure force on this side, and this pressure force will be different than this pressure force if I'm changing pressure as I move through the duct. So this is at location x plus dx. There's also a shear force, right? So there's a shear force exerted by the duct onto the fluid, right? This is a control volume on the fluid, so the duct exerts a shear force onto the fluid, and as felt by the fluid, this shear force is trying to slow it down, right? It's trying to retard the motion of the fluid, so that's in the negative x direction. And these are forces, they're not stresses, so this pressure has to be multiplied by an area. This shear force also has to be multiplied by an area. The pressure is multiplied by the cross-sectional area of the duct because it acts on this area. The shear force is multiplied by this perimeter times dx because it acts on this area that's exposed to the wall. So those are our x forces. And next we got to think about how momentum can cross the surfaces. X momentum can cross the boundaries, and then whether X momentum is stored inside of here. So we're going to do this at steady state, right? So we're not doing some kind of startup of the flow or slowing down of the flow. So at least inside of this control volume, there might be X momentum inside of here, but it's not changing with time, right, at steady state. So this storage term we're gonna not worry about, but we do got to worry about X momentum crossing these boundaries. So there's no mass flow rate crossing these boundaries up here at the surface of the duct. We're not allowing any transpiration or anything like that. So there's no X momentum there, but certainly there's mass flow rate crossing this boundary and this boundary. And we said that if I want to know what X momentum is, I have to first think about what is the mass flow rate, and then multiply that mass flow rate by U, right? So in this case, the mass flow rate crossing this boundary is the integral of rho times U times dA, right? So that's the mass flow rate crossing the boundary. If I want to know what the X momentum is, I just multiply that by U. So this would be rho times U squared times dA. So that's the X momentum crossing this boundary. I'd have to do the same integral over here, and that's the X momentum leaving over here. So this is at location X, and this is at location X plus dx. So this is a diagram showing all the different terms that I have to then plug into this balance up here, and we've done things like this many times. So here I am going to take my positive x forces, right? So this is a positive x force, and then subtract from that the negative x forces, which would be this is a negative x and this is a negative x force. So there's my sum of x forces, and that has to equal plus the rate of x momentum in, so plus this term here has to equal the rate of x momentum out, which is this term here, and again there's no storage, so that goes away. So there's our x momentum balance. We're going to shrink this control volume size dx down and take the limit as it goes to 0, which will allow us to express this x plus dx and this x plus dx term in terms of a derivative, right? So that's what I've done here. So here the pressure at x plus dx is the pressure at x times d pressure dx times dx, right? So that's something we've done several times. And then this momentum is the momentum at x plus d dx of the momentum times dx, right? And of course, as usual, these pressure terms at x cancel, these momentum terms at x cancel, and I'm left with this equation here. We're going to restrict ourselves for now. Well, we're going to restrict ourselves to the case where the cross-sectional area isn't changing in the x direction. So we have a duct with a constant cross-sectional area as the flow moves through it, which means that I can bring this cross-sectional area out of this derivative and then divide through by it. So that's all I've done here. And this is the this is the equation that I get. And it's actually exactly what I wanted, right? It relates the thing I'm interested in, which is my pressure gradient, to the things I kind of understand, which are the shear stress and the velocity distribution, right? So we can try to think about how the pressure gradient is going to behave in this internal flow based on what we understand about the shear stress and the velocity distribution. So the first thing, before we even do that though, you should recognize that, you know, the pressure gradient, this pressure gradient, first of all, it's going to be negative, right? The pressure gradient is going to be negative, which says I'm losing pressure, right? And why am I losing pressure? I'm losing pressure to overcome the shear stress that's trying to hold the flow back, and I'm losing pressure if I'm trying to accelerate the fluid, if I'm trying to increase its momentum, right? So if you go back and look at this, I'm losing pressure here because the pressure on this face has to be higher than the pressure on this face over here, right? In order to push the fluid forward. Why do I got to push the fluid forward? Because there's this force up here on the wall trying to hold the fluid back, and I have to overcome that. And the other reason I might need a pressure force is if for some reason I have more momentum leaving than I do entering, right? Those are the reasons why I'm going to need a pressure gradient that's negative. That's why I'm going to need a higher pressure on this side than this side. That's physically what's going on. All right, so let's look at sort of our mental picture of an internal flow, right? So the things we understand about an internal flow are, what does the velocity distribution look like as I move from the inlet through the developing region and then into the fully developed region, and then also what does the shear stress look like, right, as I go through the developing region and into the fully developed region. So let's start by looking at this equation out in the region where things are pretty simple, right? So if I go out into the fully developed region, what do I know about the shear stress here? Well, the shear stress becomes constant, right? So this term here no longer changes with x, right? I have a constant shear stress, and perimeter and cross-sectional area are constant. So at least the contribution of this first term is a constant. It's not saying that pressure is constant. What is it saying? It's saying that the pressure gradient becomes constant. I'm losing pressure at a constant rate, right? And then what about this term? Well, if I'm out here in the fully developed region, the velocity distribution is no longer changing. So this term here, you know, it's not changing in x, right? If I do this integral right here versus if I do this integral here, I'm going to get the same answer because I'm doing the same integral with the same velocity distribution. So d dx of that integral is 0, which is just another way of saying that the momentum I have here and the momentum I have here and the momentum I have here, it's the same. I'm not increasing the momentum. So this term goes away when I'm in the fully developed region, right? So in the fully developed region, I would expect the pressure gradient to be a constant negative value, and that constant negative value is the pressure gradient I need to overcome the shear stress, right? So this is what I get out in the fully developed region. I get a linear drop in the pressure, right? So now let's think about what happens in the developing region. So in the developing region, if I go back and look at these two terms again, the shear stress is actually getting quite a bit bigger, right? Because the boundary layer is thinner. So this first term is actually going to get bigger and bigger and bigger. What does that mean? That means the pressure gradient has to get bigger and bigger and bigger. So the pressure gradient here, you know, is this sort of nice, modest drop in pressure. If I go back here, I would expect that the pressure gradient has to get quite a bit bigger, right? And that's according to the first term. The second term is actually a little more subtle. The second term is now in play, and the reason it's in play is because I'm doing this integration, right, that gives me the momentum, but I'm doing it for different velocity distributions, right? So here I'm integrating a uniform velocity distribution, and then as I move through this entry region and get to this fully developed, you know, the hydrodynamic entry length, now I'm integrating this non-uniform velocity distribution. And it turns out that actually, even though these two velocity distributions have the same mean velocity, they don't have the same x momentum, right? And to understand that, you have to realize that x momentum is based on velocity squared, right? So in terms of velocity squared, the center core here is going to increase in velocity squared, by more than the edge decreases in velocity squared. So the center core increases in velocity by about the same amount that the edge decreases in velocity, right? Because that's what continuity is saying. But in terms of velocity squared, the center core increases in momentum by more than the edge decreases in momentum. So all that says that the momentum of this region, of this distribution here, is greater than the momentum of this uniform distribution here. And so actually, you're increasing the momentum as you move through that entry length, right? And so this term is actually positive as well. So you get a large increase in the pressure gradient due to the shear stress. That's pretty obvious. You get another increase in the pressure gradient due to the increase that has to happen in the momentum, and that's a lot less obvious, right? You have to think about it. But both things tend to give you this kind of a pressure distribution in the entry length, right? So you have this linear pressure drop in the fully developed region. You get a greater than linear pressure drop here in the entry length. This is going to give you the entry length, the entry region is going to give you a lot more pressure drop than you would expect if you were just looking at what happened when the flow became fully developed. All right, so one last thing, and that is that, in the end, we're going to look at correlations for internal flow, right? And we'll talk about where you find them and how to use them, not today, but in a later lecture. But these correlations are, the ones that we're going to use anyway are the Moody, or sometimes it's called the Darcy friction factor, right? And there's two flavors of these friction factors. There's a local friction factor, which gives you the pressure gradient at any position, right? So the local friction factor here is going to give you the pressure gradient at some particular X position, here, or maybe here, or here. The average friction factor is actually going to give you the average pressure gradient over the entire length of the pipe, right? So it's going to be the pressure at the inlet of the pipe minus the pressure at the outlet of the pipe. So these are dimensionless numbers. You can see how they're defined, right? It's an internal flow, so we're using the hydraulic diameter, we're using the mean velocity. This local friction factor is giving you the pressure gradient non-dimensionalized in this way. The average friction factor is giving you the total pressure change, right? So the pressure change divided by L is the average pressure gradient non-dimensionalized otherwise in the same way. Right, and we'll look at, again, where you find these and how they behave a little later on. But certainly how they behave in terms of flow through a pipe should be pretty obvious based on what we just talked about. Here's the pressure drop, right? Here's the pressure. So here I have, out in the fully developed region, a constant pressure gradient. So I would expect as soon as I hit that fully developed region, my local friction factor will become constant, right? Because it's based on the pressure gradient. The average friction factor, though, the average friction factor is based on the pressure difference. So one way to think about that is that the average friction factor, no matter where I am in the pipe, it always remembers this entry length, right? The local friction factor, it completely forgets about the entrance length as soon as it's beyond the entrance length, right? As soon as it hits the fully developed region, it has no idea anymore that there was this region of high pressure gradient because it's based on the local pressure gradient. The average pressure gradient, the average friction factor, no matter where I'm at, because it's based on the total pressure difference, it always remembers that there's this region of high pressure gradient at the inlet. So it will always be a little bit higher than the local friction factor, right? So if this red line is the local friction factor, it's big, but then it becomes constant right when the flow becomes fully developed. The average friction factor is big and it drops too, but it remains above the local friction factor all the time. Eventually, if my pipe is really, really long, these two things will approach one another because the impact of the entry length here will be smaller and smaller. But there's always this memory of that entry length, right? And that's the difference between these two things. And actually, unlike external flow, you can find correlations for both of these because these both might be important, right? For external flow, very rarely are you going to find correlations that give you the local anything, right? If I have flow over a cylinder, it's hard to find a correlation that tells you what's the heat transfer coefficient at some location on the cylinder or what's the shear stress at some location on the cylinder, right? Instead, you get the average friction factor, the average heat transfer coefficient and the drag force, which is an average quantity. For internal flow, there are going to be times where you're interested in the local friction factor. You want to know what's going on locally. And then there are going to be a lot of times where you're interested in the average friction factor. You just want to know what's the total pressure change, right? And you'll find correlations for both of these two things. And you have to understand, when do you want one versus when do you want the other. So that's it for this lecture. The next lecture we'll go through kind of the same type of a discussion, but we'll do it for temperature, right, and heat transfer coefficient, and hopefully try to understand how the heat transfer coefficient behaves for an internal flow, right? And then once we have that all kind of nailed down, we'll actually go look at where you can find correlations, right, and then how you use them to solve engineering problems.